These are the notes for Unit 8, Day 2, and we are continuing our discussion on rational functions. And so just to remind you that we are writing that rational function as f of x equals p of x over q of x, where both p and q are polynomials. And we're focusing today on graphing transformations. So we've done this before with various functions through the course of the year. So transformations are when we slide things up or down or left or right, or maybe we flip them or stretch them, all of that stuff. So when we talk about doing these transformations, a lot of times we focus on that parent function. So this first question here, we have a parent function of y equals x squared, right? That's the parent function for a quadratic. And so y equals x squared, then if we would graph that, if x is 0, y is 0. If x is 1, y is 1. If x is 2, y is 4. If x is 3, y is 9. And then we know that we have the same values when we square negative numbers. So squaring -3 gets us +9, etc. And so when we draw that, we get our quadratic, right? We get something that's symmetrical left to right. So something that looks like this. If you hold that down, then it will create a nice smooth quadratic. Let me scooch that point over a little bit. So there's our parent function. And so what we want to do then is we want to shift this function 2 units up. So 2 units up, if you remember for quadratics, our vertex form is a times x minus h quantity squared plus k, right? So 2 units up would be a k of 2. It's not moving left or right, so we'd have an h of 0. So this equation then would look like a is 1 because it's not being stretched, x minus 0 squared plus 2. Or we could simplify that to just say x squared plus 2. So really what we're doing then is we're taking this, I'm just going to duplicate this parabola, and I'm going to move it up 2 units. And then actually I'll make it blue just because I'm color coding here. And let's make that a little thicker. So that is the actual transformed function, x squared plus 2. So this is, I think this is probably looking familiar to you as we go through this, right? So let's try this again with a different function. So now if we go back to gray, our parent function, I'm just going to call it PF, right? Our parent function for a square root is y equals the square root of x. So if we think about that, let's just do a little table here. Right? If x is 0, the square root of 0 is 0. And now we pick special values of x. 1 is easy to square root, that's 1. 2 isn't, 3 isn't, but 4 is. Square root of 4 is 2, right? It's just a parabola on its side. 5 isn't, 6 isn't, 7 isn't, 8 isn't, 9 is. We can square root 9 and get 3. Although that already puts us off the graph. So our parent function looks like 0 and 1, and then we're all the way out here at 4 just to get up to 2, and it looks something like that. And just very similarly, let's change this to green, our vertex form of a square root function is like a times the square root of x minus h plus k, right? The h's and the k's are kind of in the same spots as they were above with the quadratic, and so is the a. So if we are 3 units to the right, that is an h of 3. So that makes this y equals, and we have an a of 1, we're not stretching it, so it's 1 times the square root of x minus 3. So look at that, and then plus 0, we're not moving up or down. So look at that. Notice that it's x minus 3 because the h is 3 and the minus sign is still there. It's a little counterintuitive. I'm moving right 3, but I see x minus 3 in the equation. So it's a little counterintuitive, right? It makes you kind of think that that's not the case. That we might be moving left instead of right, but this is actually right 3. We can simplify it like that. So I'm going to do the same thing. I'm going to duplicate this, and I'm going to move it right 1, 2, 3. So that is my transformed function. Looks something like that. Okay, so, and then we have the absolute value function, right? We did that in let's go back to our parent function. Our parent function is just absolute value of x, right? So if we did a little table here, that would be when x is 0, the absolute value of, 0 is 0. When x is 1, the absolute value of 1 is 0. When x is negative 1, the absolute value of negative 1 is positive 1. Whoops. The absolute value of 1 is 1. My mistake. So we see this symmetry just like we did with the quadratic, right? I'm just going to do 2 more real quick, right? When x is 2, the absolute value of 2 is 2. When x is negative, a negative 2, the absolute value of negative 2 is positive 2. Kind of looks like the quadratic, but there's no curvature, right? We got 0 and 0, then we got 1 and 1, and 2 and 2, and 3 and 3, and so on and so forth, and 5 and 5. I'm just going to skip around here, right? And 5 and 5. And so we end up with this characteristic V-shape function, right? That looks something like that. So that's the parent function. And just like the functions before it, the vertex form, remember the vertex we're always talking about this point or this point. That vertex form is y equals a times the absolute value of x minus h plus k. So again, the a and the h and the k are kind of in the same spots with the new function shape symbol around it, right? We've gone from squared to when I talk about function shape, we're going from squared, right, to square root to absolute value. Okay, so 2 units up again, looks like we're doing the same thing as we did for the quadratic, right? 2 units up and 3 units right. So we're moving up and right. So 2 units up is a k of 2. 3 units right is an h of 3. So we're doing both transformations that we did both above. So now we're looking at y equals, we're not stretching it, so it's 1, x minus 3 absolute value plus 2, which means what we're doing is we're taking this absolute value, I'm going to duplicate it, and I am going to go up 2 and right 3, which maybe is about right there. And let's change that to orange so I have something that looks like that. Maybe I should put some arrowheads on that. Oops. There we go. For our function that has been transformed. So that was just kind of a whirlwind tour of what we've already covered. Now we're going to do these same sort of transformations to our rational function. So here is our rational function, and so when we talk about a rational function, we have to, we're going to kind of try to use the same vocabulary as we have before. We're going to have a parent function, and so that this parent function is 1 over x. So this is our parent function right here, PF. Okay, I'm kind of jumping around a little bit, but here it is as well, is our parent function, PF. Okay, so it says graph the transformed equation in different, oh, whoops, that was for 3. To graph y equals 1 over x, fill out the table and plot the points. So we know that, I'm going to increase my pen width here, we know we're looking at x and taking its reciprocal, right? If we look at x, which is all these values, x is on the bottom, so we're taking the reciprocal of x. So negative 5 then is negative, the reciprocal of that is negative 1/5. Negative 2 is negative 1/2. Negative 1 is negative 1 over 1, or just negative 1. Negative 0.5, that's negative 1/2. The reciprocal of negative 1/2 is negative 2. Negative 0.2 as a fraction is negative 1/5. So its reciprocal is negative 5. The reciprocal of 0 is undefined, because 0 is 0 over 1, and 1 over 0 is undefined because you can't divide by 0. So that is where we have because there's 0 in the denominator, right? This is 1 over 0. So 0 in the denominator, we have a vertical asymptote, right? Remember that from day 1. Okay, so 0.2 is the fraction 1/5. Gotta be careful. A lot of people think that 0.2 is the fraction is 1/2 because they see it 2, but it's 0.2 is 20%. It's 1/5, and so its reciprocal is 5. 0.5 is 1/2. Its reciprocal is 2. The reciprocal of 1 is 1. The reciprocal of 2 is 1 over 2. The reciprocal is 1 over 5. So graphing those points, I'm going to go back to that thinner pen now. We know that we have an asymptote when x equals 0, a vertical asymptote. So that is this axis right here. So it's going to be hard because I'm writing in gray here, unfortunately. But we have that asymptote right there. So that's our vertical asymptote. And then we really kind of need some hash marks, don't we? Really can't see the grid too well. Unfortunately, you can kind of see it well. I'm going to try to zoom in. It looks like I can see it here and here and here and here. It's tough though. Okay, so when x equals 5, we're at 1/5. When x equals 2, we were at 1/2. When x equals 1, we're at 1. When x equals 1/2, we're at 2. When x equals 1/5, we're at 5. So our parent function looks like that. And we know that as x gets bigger, we have a horizontal asymptote at x equals 0, or excuse me, y equals 0. I said that wrong. So we know that this is a horizontal asymptote on a rational function. And then when x equals negative 5, we are at negative 1/5. And when x equals negative 2, we are at negative 1/2. When x equals negative 1, we're at negative 1. When x equals negative 1/2, we're at negative 2. When x equals negative 1/5, we are at negative 5. That's just the left-hand side of the table. So we have something that looks like this in the third quadrant. So basically, they look the same. It's just that one is in the first quadrant, one is in the third quadrant. It looks like actually we've taken this and rotated it 180 degrees. We have what we call rotational symmetry. Okay, so are there any asymptotes? Yes, there are. The asymptotes are x equals 0 and y equals 0 for the parent function. Okay, so now we want to move, so we want to translate this. So I am going to translate this 2 units up, 3 units to the right. So how does that look when we're talking about writing it, we can't really call this vertex form because we really don't have a vertex like we had on the other functions. But the h's and the k's kind of follow the same pattern. The h goes with the x and the k kind of hangs out on the end, right? So our parent, our I don't know if we can call it a standard form, or I don't know if you really want to call it a vertex form. I'm not quite sure what the vocabulary is here, but our function then for transformations is x minus h. Notice the x, right? The x is in the bottom, and we know the h goes with the x, so it looks like this. And then the k kind of gets tacked on to the end, because the k is only changing the y value. So we know our k equals 2, and our h equals 3. And so this, for the rational function, is going to look like x minus 3 in the bottom plus 2 off to the side there. And and so we're going to take this. I'm just trying to figure out, I think I can just grab this and this. And I'm not grabbing any of the asymptotes. That's kind of the problem there. So we have to draw in the well, let's see how I want to do this. Let's draw in the asymptotes first. Oops. Yeah, let's draw in the asymptotes first. So let's think about this. So if this whole thing is shifting up 2 and right 3, right? We're going up 2 and right 3. That means these asymptotes both have to go up 2 and right 3. So if I take this asymptote and move it up 2, it's up here at 2. So here's my horizontal asymptote. And I got to move right 3, so that would be right here. Here's my vertical asymptote. And then I can take, I want to try to grab, I don't want to replot all those points. I'm just going to duplicate this. I'm going to call it red, and I am going to move it, and it's going to go right about here. And then I'm going to give it some arrows. And then I'm going to go ahead and duplicate this one and do all the same things. And slide that over to the asymptote, right? So it's going to be right there, and then I'm going to give it some arrows. There we go. So that is the transformed rational function. And all I'm really looking at when I transform this function is, I think the most important point is right here. Right, these 2 points are, let me kind of highlight them. These 2 points are these 2 points right here, which are over 1, up 1, and left 1, down 1, from the intersection of the asymptotes. So that's kind of how I'm gauging that, and when I draw that transformed function, so that I don't have to recreate too many points. So that would be how we transform rational functions. So that's really it. If we scooch down, we'll get to learning targets in just a second. So if we scooch down in the homework, if you notice, I have you start out with the parent function and graphing that and drawing and getting that table ready. And then I start you with here. This looks like it's right 2 and up 3. So it's just the reverse of what we did in the notes. And this looks like left 4 because it's a plus, and down 2. So so it's just having you practice relocating those asymptotes and relocating those 2 curves. So when we look at our learning targets then, learning target 1 is the parent function. And then it's its transformation. It's probably the best way to write that. Okay, so the parent function, so we're looking at that parent function. So here are my x and my y axes. And, oh, that's not that good. There we go, that's a little bit better. I'm getting picky now. I'm going to get rid of that one. That wasn't that good either. That's a little bit better. Not even really that good. I want to change the thickness on this. I know I'm getting really picky here, but those are axes. Those are also the asymptotes, right? And so our parent function is y equals 1 over x. And so I am really looking to grab that over 1, up 1, left 1, down 1 point. And then I'm just going to draw this smooth curve that goes to each asymptote, right? We know we're not crossing over those asymptotes at all, and it's just a smooth curve. If you want to draw a couple extra points, I typically would draw, if you want to add a little detail, I would typically do this point at 1/2 and 2, and then I would draw this point at 2 1/2. So I would typically go after those points as well, just to get the curvature. But yeah, and so that would probably be the most that I would draw. So the parent function, then the characteristics are, we have a vertical asymptote at x equals 0. We have a horizontal asymptote at y equals 0. And y, because the vertical asymptote, because that makes the denominator 0, the horizontal asymptote, because that's where our end behaviors as x gets really far away from the origin. Whoops. So those are the reasons why. And as far as the range goes, like the range of values, right? The range is that we don't have any y equals 0s. We can't get to that horizontal asymptote. And so to transform this then, let's call it transformation. The transformations then is that this equation looks like 1 over x minus h plus k, where, and then the one in the top, I guess I really haven't talked about the a, right? Really, it's 1 times a. We could have a stretch. I'm just looking at the homework right now. I do have some stretches on the back page. So we could have a stretch there. So where a is that vertical stretch, and where h is the left or right shift, so it's the horizontal shift. I'm going to go L/R shift. And the K is the up/down shift, right? It's the vertical shift. So that's how we're going to transform it into this expression. And then learning targets 2 and 3 have to do with really the asymptotes. What happens to the asymptotes? So as you transform. So as you transform. So we know that the left-right shift is going to move the vertical asymptote, and the up-down shift is going to move the horizontal asymptote. So we need to keep cognizant of that, and then the range follows that vertical shift, the up-down shift, right? If we shift this thing up, then the horizontal asymptote moves up, and that value that we can't get to Like for instance, over, in our parent function, the range cannot equal 0. If you can make that correction there, I forgot to put the not sign there, then that range cannot equal wherever that horizontal asymptote lands, in a sense. So that really kind of covers it. So like I said, on the homework, we start out with just some horizontal and vertical shifts on page 1. And then page 2, if you notice, the A is 3 and the A is 2, so we start to have some stretches there. Here we're going to have it flip and stretch. Here it's going to stretch 4. So we're going to have some stretches there. And really, you also can rely on your graphing calculator here. If this is tough to do by hand, after you get the parent function sketched in here, you could put this in your graphing calculator just to get a level of comfort on transforming that function. That would be fine as